Yield. Yeah. Yeah.
06.
Plus 602. How many grams of carbon dioxide are required to produce 1 mole of glucose?
Okay. It's pretty straightforward stoichiometry. It's not a limiting reagent. It's just a one-step stoichiometry problem. So we start with what we know. We know that we have 1 mole of the glucose. And we're looking for carbon dioxide. So we write down mole of carbon dioxide over mole of glucose, and the ratio between those comes straight from the balanced equation. So that's a 1 to 6, 6 to 1. And so we end up with 6 moles of carbon dioxide, and they want grams. So we take 44 grams per 1 mole of carbon dioxide, and we get 264 grams of carbon dioxide.
Okay. Write it down. Yes, Kristen, I'll write it down.
Okay, any others? Okay. We're in chapter 6 talking about properties of liquids and solids, and a little bit of the gases. And one of the main differences between a liquid and a solid, liquid and gaseous water at 100 degrees centigrade is the physical state. In other words, you can have both liquid and gaseous water at 100 degrees centigrade, but one of them is different from the other in terms of the energy. It takes energy to change the physical state. We have to separate the molecules from one another. If they're holding on tightly to each other, then it takes energy to do that. Let's take a look at what's called a heating curve. A heating curve is something that plots temperature versus energy. Now, what I want here is I want a substance, and we'll take water because we're most familiar with water. And what we're going to do is to add energy to the substance continuously. A device for doing this is an oven. Thanksgiving is coming up, and if you think about it, you're going to put that turkey into the oven, and what happens? The energy from the oven, the gas that's burning in the oven, forms an energy flow into the bird. And when the energy flow causes the temperature to drop a little bit, what happens? The thermostat kicks on and the oven revs up a little bit more, gets it hotter again. So for all practical purposes, there's a constant flow of energy from that box, that oven box, into the turkey, into the bird. So that's what we're going to do. We're going to take ice, we're going to take water in the solid state at, let's say, minus 5 degrees centigrade. So we're well below the freezing point. And we're going to place it into an oven and continuously add energy. And we're going to take a look at what happens to the temperature as we do that. So when I put my ice cube into the oven, what's the first thing that's going to happen to the ice cube? Think carefully. It's not going to melt.
The molecules going to form.
It'll heat up. The first thing it's going to do is heat up because it's at minus 5 degrees centigrade. And water, ice, doesn't melt until 0 degrees centigrade. At that point, now what's going to happen to my ice cube? Now it's going to start to melt. And here's a curious thing that most people don't realize. As it melts, there is no temperature change. The temperature stays fixed. As long as I have ice, the temperature of my ice and water remains constant. You're kind of aware of this. If you buy a soft drink from Chick-fil-A or from the cafeteria, you put ice in there. Why do you do that? It keeps it cold. It keeps it ice cold. It keeps it at that temperature as long as there's ice there. Because this room is like an oven to that drink. And there's a constant flow of energy into the soda. And so what's happening to that energy? It's being used to melt the ice, not to raise the temperature of the drink. Now, once the ice is totally melted, then what's going to happen to my sample of water? The temperature is going to increase and it's going to warm up. And as it warms up, it gets to a point where it's at 100 degrees centigrade. And what happens at 100 degrees centigrade? it boils. And again, this is a phase change. As the water boils, there is no temperature change. This is something my wife does not understand. I love the woman dearly, but she's never had any chemistry. But she thinks if you put a pot of water on the stove and it's boiling, if you turn up the heat, that it gets hotter. And it doesn't. It only boils faster. It doesn't change the temperature at all. This is exactly why, and I know this has kept you up late at night sometimes, why you cannot make French fries in boiling water. When you make a French fried potato, what are you hoping to do? You're hoping to put that piece of potato into something that's going to sear the outside and form a crust. And then it bakes the inside to make the potato light and fluffy. Water does not get hot enough to do that. You cannot get water to the point where it will sear that potato. So what we have to do is we have to use a different liquid whose temperature we can get higher than 100 degrees centigrade before we put the potato in there. And that is oil. We use an oil.
Will it evaporate faster?
It'll evaporate faster if you turn the heat up. Yes, it'll evaporate faster. It'll boil faster, evaporate faster, but it won't increase the temperature. Yeah. Now, once the water is totally evaporated completely, if I've captured the steam, if I've captured the gaseous vapors, then now the energy would increase the temperature of the gas, like so. And for water, we could go up to about 2,000 degrees centigrade. At 2,000 degrees centigrade, the water will begin to break down into its elements. So that internal bond is quite strong. Okay. The reverse is also possible. If you think about it, we have a lot of humidity in the air in August. When the sun goes down and the night begins to cool a little bit, what happens? We're taking energy out of this gaseous system. And the energy is dropping this way, and the temperature of our humidity, our water that's in the vapor state, begins to cool. And at some point, it's going to condense, going to turn back into a liquid state. And as it turns back into a liquid state, at some point then the conversion is complete, then a drop in temperature will simply drop the temperature of the water down to the point where it freezes again. While it's freezing, there's no temperature change, and then when it's totally frozen, if we continue to pull energy out, the temperature will go down. Is there a bottom limit that we could get to?
No.
Yes. It's called absolute zero. It's minus 273 degrees Celsius. Pretty cold. It's the point where we think there's no energy at all left in the sample that we have.
Absolute zero?
Absolute zero.
Are you saying that water can go to absolute zero?
Well, theoretically, nothing can reach absolute zero, but they can get pretty close. Closest they've gotten is like 10 to the minus 5th degree. So that's pretty close. 0.00001 degrees Kelvin. So at that point, we're not going to quibble about whether we're at zero or not. All right. I think we talked about boiling. The boiling point is registered at 1 atmosphere. If we're on top of a mountain, the boiling point is less. If we're down in a valley, the boiling point would be greater because we are not at exactly 1 atmosphere. So the boiling point would adjust itself. We've talked about solids. We should say something else about solids. One of the things we mentioned a couple of times already is that solids form a crystal structure. And we can take a look at some crystal structures. I brought some slides for us to look at the crystal structures today. How many people actually looked at some salt? Okay. I knew you would not listen to me and do that homework exercise, so I brought some salt today so that you can dump some out and take a look at the tiny little crystals. Remember, they're not randomly shaped white particles. What you should see when you dump some out and look closely is you should see very smooth sides, sharp edges, pointy corners because of the crystal structure that we see for sodium chloride. Here is an example of that crystal structure. This is a very simplistic picture of what that crystal structure would look like, but notice the ordered arrangement. Sodium ions, chloride ions, sodium ions, chloride ions. It's actually not two-dimensional, as this picture shows. It's more three-dimensional. And so here is a three-dimensional structure of the sodium chloride crystal, showing you how it would look with, I guess, little girders or dowel rods acting as the ionic bond. The interesting thing to note is that you have you have a lot of a lot of ions arranged in the structure, but they are arranged very orderly. Look at the sodium in the center. You'll notice that it's surrounded by 6 neighbors, 6 chlorides. One to your left, one to your right, one above, one below, one behind, one in front. And so it's totally surrounded. But each chloride is also surrounded by 6 sodiums, one to your left, one to your right, above, below, in the back, and if this continued here, it would come out into the front, and we would have that complete surrounding of the particles. This is not what we would expect it to look like in real life if we were to shrink ourselves down. We would expect it to look more like this picture, where the darker spheres are the chlorides and the lighter spheres are the sodiums. But again, it shows you that perfect cube structure that you should be observing if you're looking at the salt that we passed around. Smooth sides, sharp edges, pointy corners where the corners of the cube meet. And we see that reflected in the crystal structure of sodium chloride. Now, a lot of solids form crystal structure, but they're not all the same. Here is a slide that shows how some solids will form different crystal structures. Oh, it's a very good slide. So clearly. Well, anyway, let me tell you what's on here. This is the sodium chloride crystal structure, which looks very uniform from your point of view. There are ones that look very complex from our point of view. Where's the slide? Let's not talk about it. I don't know if these other ones will show up or not. There are some interesting types of substances that we can make. Sand, for example, otherwise known as silicon dioxide, is a type of crystal structure, but this one is more covalent crystal structure. These bonds that you see, these little black lines, are actual covalent bonds that exist between a silicon and some oxygens. And it's a 2-to-1 ratio. But this forms what's called a network covalent solid. This is a very strong type of substance. It's got covalent bonds, which you know are fairly strong when they're internal bonds. And so is sand quite a strong substance? Next time you're at the beach, pop a few grains in your mouth and grind down. Don't really do that, okay? I'm not paying your dental bills. But if you've ever had that experience, you know that it's pretty hard type of stuff. Think about it. We glue it to paper and use it as an abrasive, a sandpaper, to run down wood and metals and so forth because of its hardness that results from this type of bonding. There's another substance that bonds in this fashion. Carbon atoms will bond in this way with a continuous covalent bonding to itself. It turns out that carbon has the perfect bond angle. It has the angle of a tetrahedron, and the 3-dimensional structure that results is sort of like the perfect solid. Any guess as to what this is? This is diamond. Diamond is nothing more than the element carbon, the same as the ashes from a campfire, soot from your fireplace. It's just a different solid structure, crystal structure for the carbon. But it's pure carbon, and in this tetrahedral bonding structure, it makes the hardest substance known to man. And so this becomes an excellent abrasive. Now, there are some quirks of the carbon that says it doesn't have to bond in that fashion. This is another bonding form of carbon called graphite. Graphite has carbon atoms that are very strongly bonded in a plane, and then they're weakly bonded between the planes. So it's kind of like this stack of slides right here. I have these slides, and the slide itself is quite strong. You can't tear it apart easily. But if I stack them, there is an attraction from one slide to the other, because when I go like this, they don't just slide off of each other easily. But if I supply a little bit of pressure, notice how they peel off quite easily. And this is exactly what graphite does. And so one of the uses for graphite is it's an excellent dry lubricant for things like locks, where you have metal rubbing on metal, and there's normally a lot of friction there. And so if your key sticks in your home lock, you can go to the hardware store and buy a little tube of graphite, give a little squirt in there, and it lubricates the metal. So the key slides in much, much more freely. And it's because now the graphite's sliding on each other, and it allows for that metal to just slide very, very easily with respect to the other metal because of the graphite that's in between them. My kids, when they were younger, were in Scouts, and Scouts have this event called the Pinewood Derby. And the key to a Pinewood Derby winning car is to polish the axle and to graphite them with some kind of dry graphite lubricant. And if you do that, you have a good chance of being a Derby winner. Notice that graphite is exactly the same chemical composition as diamond. Graphite is what you find in your pencil when you write with it. And what happens when you write with a pencil? You supply a little bit of energy. You push down on that pencil, and what happens? Those layers of graphite peel off and become attracted to the paper. How do I know they become attracted to the paper? Because if I pick up the paper and do this, the graphite doesn't fall off. It stays attracted to the paper. But it's not strongly attracted to the paper. If I have a little piece of rubber called an eraser, I can rub it over the graphite, and the graphite becomes more attracted to the piece of rubber, leaves the paper, and adheres to the rubber eraser, and I can erase a pencil mark from a sheet of paper. Since carbon is the same element in both graphite and diamond, when I got engaged, I tried to convince my wife that a graphite ring was every bit as chemically sound as a diamond ring, but I told you she's never had any chemistry, so she didn't buy that from me. Probably for good example. Okay, any questions? Good, we move on to chapter 7. Chapter 7 deals with solutions, and it's our last chapter before our next exam. So hopefully by the end of today, we'll talk about the next exam and set up a date. But there are some parts of chapter 7 we're going to skip. So the ones I want you to spend your time on is sections 7.1 to 7.5 and section 7.7, but no calculations. Okay, we're not going to do the math that's in 7.7. We're going to do the math that's in the other parts, but not the math that's in 7.7. So, what is the title of chapter 7? Well, the title is Solution. And probably we have a feel for a solution already. I'm willing to bet that when I say the word solution, most of you are thinking something wet. Okay? But like many terms that we've been acquainted with before, when we get to a chemistry class, we have to be a little bit more specific about what these are. We know that if we dissolve salt or sugar or even a gas into water, or any liquid for that matter, that we would say we have a solution that forms. But the term solution is a little more general than that. I could dissolve one metal inside of another metal. It produces a substance sold in the stores as a solder, and it's used for electrical connections. And that's actually a solution, even though it's in the solid state. The air that we're breathing right now actually is technically defined as a solution. It's a mixture of substances in a homogeneous fashion, and that's what our solution definition is going to be. It's going to be a homogeneous mixture of two or more substances. And if those substances involve a liquid, so be it. That's probably the more common form of solution, but it doesn't have to be. As I pointed out, we could have a solid solution, we could have a gaseous solution, we could have mixtures of the physical phases all the way around. The solution is made up of several components. There are two important components in every solution. There is at least one solute. There could be more, but there's at least one. And the solute is defined as the substance that gets dissolved. And there is one solvent. There's only one solvent in a solution, not two. And that's the substance that does the dissolving. So the most familiar example to us are water solutions. And in water solutions, 99.9% of the time, water is the solvent. And we're dissolving something in the water. Salt can be dissolved in water. Sugar can be dissolved in water. There's lots of chemicals that can be dissolved in water. And all of these make a solution. Can I dissolve both sugar and salt into the water?
Yeah.
Yes, so I can have a solution that has more than one solute. And it doesn't have to be a solid. Can I put a gas into water? Think of a carbonated beverage. It's nothing more than carbon dioxide gas that's been dissolved into that water solvent. So, when you have a liquid and anything else, the liquid is the solvent. But what if you're dissolving two liquids together? Suppose I have an alcohol and water mixture. Then we generally assign the term solvent to the one that's present in the larger amount. So if I were to put a drop of alcohol into a liter of water, the alcohol would be my solute, the water would be my solvent. But if I took a drop of water and added it to a liter of alcohol, then those roles are reversed. In that case, the water is the solute and the alcohol the solvent. What if I had a 50-50 mix?
Then you have a mixture.
I do have a mixture. In either case, I have a mixture. They're all mixtures. But a 50-50 mix, it would be up to you to state, this is what I'm considering to be the solute, this is what I'm considering to be the solvent, if you're trying to define something or make a calculation.
So,
Yeah.
in the 50-50 mixture, you said either one could be a solvent and it'll be
Your call.
correct? Okay.
Okay. Or my call, if it's a problem, I might tell you what it is, but generally the person making up the solution gets to declare what it is. They're not too common. All right, when we talk about solutions, we're also talking about what are called true solutions. Let me give you an example. Suppose I bring in a liter beaker of water. Most of you have had the laboratory, you know what a liter beaker looks like. I'm going to get some nice, cool, clear, distilled water and bring it in here. Then I'm going to step out that back door where there's some bushes and grab a handful of clay and come in here and throw it into the beaker and quickly stir it up and say, look, I have a clay solution. But what's going to happen after a few minutes? It's going to settle. It hasn't dissolved in my solvent. And that's what we would call a non-true solution. So in a true solution, the solute has to dissolve into the solvent. It has to be mixed together in terms of individual little particles, whether they be ions or atoms or molecules, but on that kind of level, on the molecular level, we have to get that kind of mixing. Clay particles are just much too large, and gravity will cause them to separate out from the solution and lay on the bottom, and so we don't have a true solution. Another example of a non-true solution is like oil and vinegar salad dressing. Now this isn't quite the same. This is a water layer with a substance called carbon tetrachloride. Carbon tetrachloride is a dry cleaning fluid. The carbon tetrachlorides on the bottom, I've colored the water with a chemical dye so that we could see them separate from one another. And they form a non-true solution in the sense that they don't mix with each other. The carbon tetrachloride and the water do not dissolve in one another, so they form a two-layer system. Now, I can shake them up and say, hey, look, carbon tetrachloride water solution. But I have to say it fast because what's going to happen as this sits here for a little while? It's going to end up separating again. And we're going to see that all the blue is going to rise up to the top, all the clear is going to sink down to the bottom, and we have effective separation. So we never really had a true solution in our hands to begin with. Solutions depend upon solubility. Solubility is a chemical term that talks about how much stuff will dissolve in the solvent. So suppose I have my liter beaker of water again. And let's suppose I take that salt that's being passed around and dump some out on the table, and I take one tiny little grain, one of those little white cube grains, and I pop it into the water. Do I now have a solution? Yes, I do. That salt is going to dissolve into that water. If I put a couple more grains in there, do you think those will dissolve? A couple more? What if I put in a shovelful? Will all of it dissolve? No. Solutions are very much like you on Thanksgiving Day. What happens? After a big meal, you say, well, don't give me any more. You put any more turkey on this plate, and I'm just going to let it sit there. It's not going into my mouth. Okay? And that's what the solution says. You put any more salt into me, and I'm not going to dissolve it. It's going to sit on the bottom of this beaker. At that point, we say the solution is saturated. We have saturated our solvent with as much solute as we possibly can. Before that point, we would say it is unsaturated. Now, these terms depend upon conditions. If I have salt dissolved in water to the point of saturation at room temperature, if I heat that water to boiling, might I get more salt to dissolve?
Yes.
I might. Okay? Yes, ma'am.
So saturated solvent is when it can't dissolve and the solvent can't dissolve anymore.
Saturated solution is when the solvent will not dissolve any more of the solute. Now, I think earlier this semester I showed you a case of supersaturation. And that was one of those cases where I was able to heat the solution up to a higher temperature, get more to dissolve, and when it cooled back down, it didn't precipitate the extra solid like we would expect it to. But we triggered it, and it did, and we linked it to energy and showed that energy was being given off in the process. And so supersaturation is a condition that does, in fact, exist. Now, most solids will increase their solubility with an increase in temperature. But they vary a lot. Sodium chloride, ordinary table salt, is remarkably not one of these that increases much. The amount of salt that changes from freezing, at freezing temperatures, 0 degrees centigrade water, you can dissolve 35.7 grams of salt in 100 milliliters. So about 35, 36 grams. At boiling water, you can dissolve 39.8, so about 40 grams. So it's only about a 3 or 4 gram difference between freezing water and boiling water. Sodium acetate, the stuff that we use for the supersaturation, is hugely different. At low temperatures, we can dissolve some sodium acetate. I don't have the numbers, but at high temperatures, many, many times that amount can dissolve. So we're not talking about just 3 or 4 grams more. We're talking about maybe even hundreds of grams more that could dissolve into a 100 milliliter sample. Silver nitrate, 122 grams will dissolve in 100 milliliters of water at 0 degrees centigrade. At 100 degrees centigrade, 952 grams will dissolve in 100 milliliters of water. A huge difference for silver nitrate compared to sodium chloride. So it just varies from substance to substance depending upon the interactions that are taking place in the dissolving process. In contrast, gases exhibit the opposite behavior. All gases follow this regulation. Gas solubilities decrease with increasing temperature. If I have hotter water, I get less solubility for gases than I do if I get colder water. This makes sense to us in some cases. If you're a fisher person, when you go fishing, where do you look for the fish? You tend to look in more shaded, cooler areas. Why? That's where the oxygen is. The oxygen will dissolve more in cooler water than it will in warmer water. So if the water's been sitting out in the blaring sun on an August day, that's depleted a lot of the oxygen, and the fish find it hard to breathe through their gills in that kind of water. So they go for cooler, shaded water places where the oxygen might be greater. When I was a kid and you went to the store to buy a goldfish, they would put it in a little plastic bag with water for you, and you would take it home. And what would they tell you to do? Would you put it immediately into a bowl of water? No. Why not?
Because they got it adjust.
No, not a temperature change. The reason is that tap water in our areas are treated for bacteria. They save our lives. They treat the water for bacteria that might be found in natural water sources. And that's done with an oxidizing agent. Okay? That's not harmful to us. We take a glass of water, there's a little bit of oxidizing agent in there, we can live through it. But the little fish is so much smaller, and he lives in the water. Okay? That would be harmful to the fish. So they tell you to boil the water first. Boiling the water gets rid of the chlorine that might be in there that could cause harm to the fish. Now, you don't put the fish in the water right away because he would fry. Okay? You'd have boiled fish for dinner. Yes, that's right. Poor little goldfish. But even after it cools back down to room temperature, they tell you do not put the fish in the water at that point. Why? He will die. If you put the fish into water that has been directly cooled from after boiling, the fish drowns. Crazy as it sounds, but what you've done when you boil the water is you got rid of the chlorine, the oxidizing agent. But you also got rid of all the oxygen that's in the water. It's a gas. And at boiling temperatures, the gas solubilities are 0. So you've gotten rid of all the oxygen. So if you put the fish in too quickly, he doesn't find any oxygen. He literally drowns in the water. So what do? They tell you let the water sit overnight. And now oxygen from the air will redissolve in the water, but the chlorine is gone, and that's not a problem. And so in the morning, it's safe to release the fish and put them into the water. Or I think nowadays they sell you drops that you can put in, bonk, 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 and you don't have to worry about any of that. But life was just so much tougher when I was a kid than you got it today. Like those U-verse commercials, right? You sit by the TV, by God, in the living room. Anyway. Okay. Nuclear power plants experience this problem. When nuclear power plants were first built, they were all built on water sources, lakes or rivers. And the reason is that they use water for the production of the electricity. The nuclear power plant supplies the energy, which actually boils the water. The boiled water turns to steam, and steam drives the turbines that create the electricity that we use in our homes. When they're done with that water, what would they do? Put it back in the river or the lake or wherever they got it from. But in the initial stages, they were putting back the water at a much higher temperature than they were taking it out. And because of that, the oxygen was depleted. So downriver from the plant, all the fish life and marine life and plant life and everything was dying because we were depleting the oxygen from the water and putting it back in as a source, and they couldn't survive. So what we did was we built what are called cooling towers. Now when nuclear plants are finished with the water, they send it up a tower and have it spiral down, radiating a lot of that heat, getting back to the temperature at which it was taken out, and also an aeration. They blow air into it so that you get the oxygen back into the water so it doesn't affect your plant life downstream, even though you've used it for producing the electricity. Increased pressure has little or no effect upon liquids or solids dissolving in a solvent. So salt in water, if I put some extra pressure on top of that solution, the salt's just going to laugh at me and not do anything other than it would anyways. So it doesn't have any effect on liquids or solids. But pressure does have a significant effect upon gases. Soft drinks are bottled under increased pressure. We know that soft drinks have carbon dioxide present in them. And when they're manufactured, that carbon dioxide gas is pushed into the solution, and they put in extra and before they put the top on. How do we know this? If you take a bottle of Coca-Cola and slowly open it near your ear, what will you hear? You'll hear the hiss. You'll hear an escape of gas. And that's the extra pressure that is in that sample. Now, when we do that, we have a bottle got some liquid in there, and there's carbon dioxide gas that's dissolved in this liquid. And there's carbon dioxide gas that's up here. As long as I have them together for a period of time, they establish what's called an equilibrium. The carbon dioxide gas dissolves, some doesn't, but they go back and forth. Some of the gas is constantly dissolving, some of the gas is constantly coming out on a very microscopic scale. When I open that top, however, when I open the top here and you hear the hiss, all the gas up here escapes. The CO2 gas comes out of my container. And now the pressure has been relieved. It's less than it was, which means there's carbon dioxide gas dissolved here that should not be dissolved at that new pressure. And so what's the observation we make when we first open the bottle of a soft drink? Bubbles. We see the bubbles come up. And the bubbles are the extra carbon dioxide gas that is trying to escape from the solution because it no longer has the high pressure that was there holding it in the solution. Now, as we leave it sit out on the table, it continues to bubble. Why? It's warming up. And as it warms up, what's the solubility of the gas? Less than it was when it was cold. And so it continues to drive out the carbon dioxide. And if I leave it sit here long enough, what happens to my soda? It goes flat. All the carbon dioxide is released and gone. Anything we can do about that? If you're a 3-liter Thirst Buster drinker of Coca-Cola, you know that you buy it and it looks like this when you start. Okay? And there is a equilibrium that exists between the carbon dioxide in the solution and the carbon dioxide in that little tiny airspace. Remember, we have to leave that little tiny airspace so the liquid can expand without breaking the bottle. When we open it up and take a drink, like so, we drink some of it out, and then we cap it up again and put it in the refrigerator. What happens now? It has to establish equilibrium again. And since we've let all the carbon dioxide go that was up here in the airspace, more of it has to come out. So the second time you use the bottle, does it taste as refreshing, as carbonated, as it does the first time? No. And in fact, the further down we get, over time, lunch, dinner, late night TV, tomorrow's breakfast, okay? What happens? This gets flatter and flatter and flatter. Why? Because more is needed to establish the equilibrium here. So what could we do about that? One thing we could do is squeeze the bottle. They make bottles that are corrugated. Have you ever seen these?
Yeah.
And so the idea here is that when you drink some of the soda out, you collapse the corrugation of the bottle so that you establish a smaller airspace. Keeps in the carbon dioxide a little bit better for a little bit longer. Late night TV sells fancy little pump things that you can put on here that you pump up the pressure again. They don't do a thing, okay? Because think about it, you're trying to establish an equilibrium between the carbon dioxide that's in the liquid and the carbon dioxide that's in the airspace. When you use the little pump thing, what are you pumping back into the bottle? Air, not carbon dioxide. And so it has absolutely nothing to do with the carbon dioxide equilibrium. If you put more air in there, it will still establish the same equilibrium with the carbon dioxide. How can they sell something like that and make it sound legal? Well, I guess since we exhale carbon dioxide, is there a tiny percentage of carbon dioxide in this airspace? So when you pump this up, you are putting a little, almost infinitesimal amount of carbon dioxide in there. So would it save carbonation? In theory, it would save it a little bit, but in practice, you're not going to notice that little bit at all. So bad device. Don't waste your money. Now, grocery stores sell dry ice. What is dry ice? It is solid carbon dioxide, and it undergoes a sublimation process. It goes from the solid to the vapor. So theoretically, now listen carefully here, theoretically, could we put a piece of dry ice in here and have it increase the carbon dioxide amount and reestablish the carbonation? Why do I tell you not to do this? you don't know what you're doing, and you put in too big a piece of carbon dioxide, you will create so much gas, it will explode the bottle. And you don't want that to happen, because it could be physical injury involved in something like that. So, unless you're an excellent stoichiometry problem solver, and I've checked the grade book, there's no excellent stoichiometry problem solvers there, don't try that experiment. Okay? Don't put carbon dioxide, dry ice into a closed vessel.
So talk to us about Mentos and Coke back there.
Mentos and Diet Coke. The operation, as best I understand it, is that it releases the carbon dioxide that's in the Coke. Okay, it'll do it with regular Coke or Diet Coke. The reason they use Diet Coke is it's so messy, Diet Coke becomes very sticky and gummy, or a regular Coke becomes sticky and gummy because of the sugars, Diet Coke does not. But I think what happens is if you look at that mint, it's very porous. And porous means a lot of surface. And the release of bubbles is usually surface dependent. A lot of times when you pour soda into a glass, where do the bubbles form? Around the edge. They're on the glass, on the walls of the glass and so forth. Scratches in particular, because it's a rough surface. And the Mentos offers that rough surface. And a brand new bottle of Coke has a lot of carbonation, so that when you place those Mentos in there, it releases so much carbonation at one time, it's like a jet stream. And it blows it out. It's pretty, you've done it.
My daughter.
Wow. I wish you'd call. I'd like to see it all over your kitchen. What if I don't what?
Just leave it.
Should be fine for the most part. Now, how long a period of time are we talking about? A glass or a bottle?
And I had it like good.
But it's open? It's a glass that's open?
No, it's not
Okay.
open. A glass bottle.
A glass bottle, so it's been sealed by the company. And you've had it for a long, long time. The carbonation should still be there. Unless there's a faulty seal, that carbonation should be there. However, some of the components of soft drinks will degrade over time. Like if you keep Diet Coke around for a year or two, it gets sort of a funny taste. I do all kinds of experiments. And so I would guess that there might be some funny taste to the Coke if you decide to open it. But you should still see bubbles when you do that. If you decide to try that this weekend, we want to report on the results.
Does a soft drink go flatter if it's left sitting out or if it goes back in the refrigerator?
If it goes back into the refrigerator, you have a better shot. Because a couple of reasons. One, you're probably going to put the lid back on. And as soon as you put the lid back on, you allow it to reestablish its equilibrium without escaping CO2. You're also decreasing the temperature. And gases have a greater solubility at a greater temperature. And so there's more carbon dioxide that will remain dissolved under those conditions. If you leave it out in an open glass on the table and it warms up to room temperature, the carbonation probably will not last that long. I mean, there's certainly a time lag in there. If you're having a conversation with somebody, but you come back the next day, I would expect it to be pretty flat by that time. Okay. Deep sea divers are another example. Deep sea divers go down into the water, and what happens is that in our bloodstream, there's a certain amount of nitrogen dissolved in the blood. 80% of the air we breathe is nitrogen, so it's in our system, it's in our lungs and so forth. And it dissolves into the bloodstream. The blood is basically a liquid, a water-based fluid, and it will dissolve nitrogen gas into the blood. When we increase the pressure, remember that increases the solubility of gases. When you dive down into the water, if you're a swimmer and you've done this, you go down deeper and deeper and deeper, what happens? Your ears start to hurt. The pressure gets to you. What's happening is there's a lot of water molecules above you pushing down on your tiny little frame, and it starts to push you in. Well, it pushes those gases into a smaller area, making them more concentrated, making them dissolve more into the blood. That's not a problem. That's okay. The problem is if you come up too quickly. If you now come up too quickly from a depth that you've been down for a while, where the nitrogen's been dissolved for a good long time, and you come up very quickly, it's like opening the bottle of Coca-Cola. What happens to that extra gas? It forms bubbles. And bubbles in your bloodstream are not a good thing, because our blood flows through very tiny areas called capillary tubes that allow the blood through almost like one blood cell at a time. And if you've got a bubble in there, what happens? It blocks that flow. And that flow leads to a problem called the bends, which is a blood flow problem, and in fact it can be fatal. So what do? Well, divers are trained to come up very slowly. By coming up slowly, if they've not been down too deep or for too long, by coming up slowly, the nitrogen is released, but not in bubble form. It's released in more microscopic form, and they're okay. If they are down for a long time and have to come up, what do? We put them in what's called decompression chambers. These are rooms where the atmospheric pressure is increased greatly, like it would be down in the depths of the ocean. And then that pressure is slowly released over a long period of time, again, giving the nitrogen a chance to come out without forming bubbles.
Is that a hyperbaric treatment?
Yeah. So why do substances dissolve at all? Seems like a curious thing. Clearly not all substances do dissolve. Things like our skin doesn't. Good thing. Because if we took a shower in the morning like we're supposed to, we would be wiping off our skin every day, or if we were caught in a rainstorm, not a good thing. So other substances do dissolve, but why do some dissolve and some not dissolve? And why do they dissolve in different solvents? Well, chemistry's got the answer for it. We need to consider what the molecules are doing. The molecules are interacting with each other. There's a solute-solute interaction. Remember, we've talked about this in the last chapter. Water will hydrogen bond with itself. It's attracted to its neighbors because water is a polar molecule. It has a dipole, and we have that dipole-dipole attraction. And so if I have a sample of water, remember, here's the water molecules. And here's another one. And there's an attraction between the hydrogen of one and the oxygen of another. And I've got another one over here, and so an attraction takes place there. I've got another one over here, and attraction takes place there. So every water molecule is probably attracted to 3 or 4 neighboring molecules. So there's that interaction between the, in this case, the solvent particles. Solutes are doing the same thing. If I have let's take HCl. It's a gas, but there's weaker interactions between gases because remember those particles are very far apart.
You said there's a solute interaction.
There are solute-solute interactions and solvent-solvent interactions. Okay?
What is it for? The solute?
We're deciding how something actually dissolves. So let's take the case of water and HCl. Now water is a polar molecule, and it's a polar molecule that is one of the few that has hydrogen bonding, that special case where hydrogen is attached to a highly electronegative element. And so you can see the interaction that's taking place in this beaker of water that's right here. Now HCl is also a polar molecule, and it has a positive end and a negative end like this. My goal here is I'm going to place some of the HCl into the water to see what happens. So I have this beaker of water here where what's happening? All the water molecules are joyous. It's like a Christmas party where everybody's interacting with each other, right? You're talking to this person for a while, and then you move over and talk to this person. You're interacting with different people at the party, but always interactions taking place. So the water molecules in their water sample are having a good old time. Now, what are we going to do? We're going to introduce a foreigner into the mix. We're going to plunge an HCl down, boom, into the water. And what happens? 2 water molecules that were interacting with each other, all of a sudden, bam, something's between them. How do they react to that foreigner? It depends on the foreigner. If the foreigner is polar, like HCl, with a positive and negative center, the HCl says, look, Waters, I know I've torn you apart from each other, but I'm offering you the same kind of interaction. So I can get the same kind of interaction to take place because the HCl is a polar molecule. And so will a water molecule come along and interact with the hydrogen and the chlorine that's there? So yes.
Yes.
Will the oxygen part of the water come along and interact with that hydrogen from the HCl?
Yes.
So as long as they have the same type of interaction, they're very tolerant of the foreigner, and they say, okay, you can stay. Okay? So now let's consider another beaker of water, and we'll bring along something like carbon tetrachloride, CCl4. Yes, the carbon-chlorine bond is polar, but the tetrahedral geometry of this molecule is a perfect geometric shape where everything cancels and the molecule is nonpolar. And if it's nonpolar, it doesn't have a positive and negative center. So what happens when we say to the water molecules, here, accept this foreigner, and plunge down a guy that has no positive and negative centers? He says, look, Waters, I know you're interacting with each other nicely, and I've got nothing for you. Then what do? They literally push that guy out of the way so they can get back to interacting with each other. And they'll push him into his own layer. So that's exactly what's happening here, is that I'm placing the nonpolar carbon tetrachloride into the water, and the waters are saying, oh, no way. And they're going to push it into its own layer, depending upon the density. The density of carbon tetrachloride is greater, so it's going to go to the bottom. Water, if you look really closely, you can see them pushing. No, you can't. But you get the general idea. Now, what this means is we have a general rule of thumb. Polar solvents dissolve polar solutes. Polar solvents will dissolve polar solutes. Nonpolar solvents will dissolve nonpolar solutes. But the two don't mix. So the rule we have is very simple. We usually state like dissolves like. And what does that like refer to?
The charges.
The polarity of the molecule. That's why we spend time determining whether a molecule is polar or not. Because we need it when we start talking about solutions. Is this a polar molecule? Should it dissolve in water? Yada, yada. We make that determination. Like dissolves like. No. Shouldn't. You might get it to mix a little bit faster and separate a little bit faster because the molecules are more energetic, but no, I would not expect it to dissolve in water.
Question.
Yeah.
So you said non-polar solvent will not dissolve a polar solvent?
I will say that, yes.
Okay.
I'll give you some examples. Brand new car. You just got a brand new car. You drive it home and the road there that's between you and the car dealer has just been paved with tar. And you get out and you look at your brand new yellow car and there's tar all over the side. So what do? You get the hose out? Take it off? Why not? Tar is a non-polar organic material. Okay? Water is polar. The two don't mix. What could you use to get the tar off your automobile?
Some type of
We can use something that's non-polar.
Yeah.
Gasoline is a non-polar liquid. You know that because water and gasoline don't mix. So gasoline could be used to take the tar off your automobile. Very careful, because gasoline has another chemical property called combustion. So you don't want that cigarette hanging out of your mouth while you're using the gasoline to take off the tar from your automobile. Also, most of the coatings on cars can tend to be non-polar. Freshly waxed car. What happens to water on a freshly waxed car? It beads up. Because why? It doesn't like the wax. It doesn't interact well with the wax. And so it'll slide right off the car. Okay, well, if you use gasoline to take off the tar, then you're also taking off the nonpolar wax coating, and maybe the clear coat, and maybe the paint. So proceed carefully when you do that sort of thing.
Different chemicals. I know that sometimes you can use gasoline to take something off, and then take maybe layers of thing off.
And sometimes-
Kerosene won't.
Yeah,
And
different
it's
things. So
just-
you might try mineral spirits.
Or acetone.
You might try acetone. You might try some of those orange cleaners that have other organics in them. The same problem is with sales labels. I think at Walmart and Kmart, they train their people to
Oh,
put that
God.
sticky label on the most obvious spot of the item that you buy, right? And then you peel it off and it's got the gum underneath, and water just doesn't do that because the adhesive is an organic material. What can you use to take that off?
Alcohol.
Acetone works very well. Acetone is a nonpolar,
You have to be careful because acetone will melt.
it'll
plastic.
mess up the plastic if your item is soluble in acetone. So you need to be very careful when you do that sort of thing. So yeah, there are issues, there are problems with it. Yes, ma'am. What are you saying?
To go back over that again, how do substances dissolve? And pretty much you said that if it's a polar solvent, it would dissolve with a polar solid.
Like dissolves like, yes.
And, non-polar do non-polar, but they don't mix together, but that's why they dissolve, right? So what about, and why some don't is because one will be non-polar and one will be polar.
That's a general rule, okay? Now, there are some cases with ionic materials, like sodium chloride dissolves very well in water. Ionic, remember, is an extreme of polar. If we have something that's ionic, we know it's polar, because it's an extreme of polar. Okay, so sodium chloride dissolves well in water, but not all things do. Silver chloride does not. And the problem is that it's a lot more complicated than we're presenting. There are energies to consider between the silver and the chloride. What's that bond energy? If that bond energy is greater than the bond energies that will result from the interaction between those guys, then it's not going to happen. And with silver chloride, it doesn't happen. With sodium chloride, it does happen. So not all substances will dissolve, even though they are ionic or polar into a polar substance. But the general statement is true. Like dissolves like. Most polar substances will dissolve in most polar solvents. Most non-polar substances will dissolve in non-polar substances. So here's an interesting little application. I have a piece of styrofoam, very non-polar. You know that because it doesn't dissolve well in water. We are able to keep our styrofoam tucked away very nicely in a small bottle like so, so that we keep it out of harm's way. Okay, how did I do that? There's acetone in here. Acetone is a marvelous solvent for styrofoam. And you saw that it'll dissolve as fast as I dunk it down into the acetone that's in the little bottle. So, take it back up. You don't want to see it
That would be amazing.
at this point. Okay. Now, how does this dissolving take place? Let me go back to a slide that we had here earlier, and we can actually show that process taking place. This is sodium chloride. Remember we said that if you put sodium chloride in water, we would certainly expect it to dissolve. Okay, again, why? Because there's a bond between the sodium and the chlorine making that crystal structure, and that bond has some strength. But if the interaction between the ion particles and the water are a greater advantage for those particles than staying together, then they're going to dissolve. And so here's that slide showing you the crystal structure of sodium chloride, with the darker spheres being the chlorines, the lighter spheres being the sodiums. Let me show you what would happen if I put this into water. If I put this into water, then what I'm expecting to happen here is the water particles are going to start to interact with this crystal. They're going to immediately start to surround it. Now they don't do this randomly. There's a method to their madness. This is a chloride. Chlorides are positive or negative?
Negative.
Negative. Look at how the water is orienting itself with respect to that negative chloride particle. It's the hydrogen ends pointing in. Sodiums are
Positive.
positive. Look at the water orienting itself with the sodium particle. The negative end is pointing in. And we see that all the way around the crystal. Now this interaction, we call it solvolysis. An interaction between the solvent and the solute. It's got a couple of names. Solvolysis, salvation, not salvation, solvation, or hydration if it's water in particular. That interaction is sometimes strong enough to pull these guys apart. Look, these guys have been whooshed away. You can't see it on this slide, but there are little lines here that are whoosh, whoosh, whoosh. You can see a little bit of whoosh. Okay? That thing is coming away, and look how it's surrounded in the water. Again, not randomly, but this is a negatively charged particle, and the waters have all their hydrogen ends pointing inward. The sodium particle, whooshed away, has all the waters with their oxygen ends pointing inward. So we see this interaction that takes place is very important for the dissolving process.
Dr. Braun?
Yeah. Here's
Um,
another little slide if you want to take a look at that backwards.
when salt is in its solid, like the solid form, not dissolving, and
Right.
you crush a crystal,
Right.
is that just breaking the bonds? It's still like
Probably you're
sodium
breaking
and
some of the
chlorine?
ionic bonds with brute strength, and then you're forming smaller little crystals.
Oh,
Okay, even those crystals look powdery under a microscope, they would still retain some of their crystal structure. Okay, so here's an HCl case like we had described on the board before. And here's the HCl particle still intact, surrounded by the water molecules, again with the correct orientations. And then a lot of them get split apart. So here's the chloride ion split apart, hydrogen ion split apart. And look at the water orientations around each of those particles. It depends upon the charges that are present. And so like dissolves like becomes a very powerful rule for dissolving purposes. Again, not foolproof, but very powerful.
So except in ionic, is that like the exception or?
No, ionic follows that general rule. Remember that ionic is mostly polar. But there are some ionics that don't follow it. So again, it's a general rule, it's not a total fail-safe. There are some substances that just say, no, I will not dissolve. Okay. And there are substances that are nonpolar like that too. Diamond, for example, doesn't dissolve in much, even in nonpolar solvents, even though diamond is very nonpolar. The covalent bonds are just too strong, and so it doesn't break apart very easily. All right, we have some terms. If solids dissolve in liquids, we call them soluble.
Soluble?
Soluble, S-O-L-U-B-L-E.
What is it again?
If solids dissolve in liquids, soluble. If solids do not dissolve in liquids, we call them insoluble. If liquids dissolve in liquids, we call it miscible. Although we sometimes error and call them insoluble, but the correct term would be miscible for liquids. And if the liquids do not mix together, like our carbon tetrachloride and water bottle here, then we'd say they are immiscible liquids. So alcohol and water is totally miscible. How do I know this? I've done a lot of experimentation. Okay? You go to a bar, order a drink, mix it up, then taste that drink with a straw from the top, from the bottom, from the left, from the right. The alcohol content should be the same in all places because it's totally miscible and mixes throughout the sample. Try that with oil and vinegar salad dressing. Shake it up, let it sit for 10 minutes, and then try it with a straw. Will the top and the bottom taste differently? Very much so, because there you have separations.
You said if a liquid does not mix, they're immiscible.
Immiscible, we put an I in, like impossible. Okay, there are some factors that will help with the rate of dissolving. How quickly does something dissolve? And that's a different issue as opposed to whether it dissolves or not. The other issue is how fast does it dissolve. Particle size. If I have a big piece of rock salt, or if I have salt that I've powdered into tiny, tiny crystals, which one will dissolve faster?
The smaller pieces.
The tiny crystals, because it's a surface phenomenon. You get more water around those crystals. With the big piece of rock salt, the only action is on the surface of the rock salt. The salt guy in the middle can't say, oh, I think I'll dissolve. He's got to wait until he comes in contact with the solvent. So particle size has a lot to do with the speed at which something will dissolve. Agitation helps. If I dump salt into water and it sits on the bottom of the glass and slowly dissolves, it's going to take a while. But if I stir that solution, it goes faster. The reason is I establish those little local equilibriums. If I've got solid here, liquid here, then there's a little equilibrium that goes on here, and they're not spreading out quickly throughout the solution. In fact, this makes for a really neat magic trick. If you want to trick your kids, I'll show you how to do this. Prepare a saturated salt solution. Mix salt into water until it will no longer dissolve. You might want to let it sit overnight to make sure that there's still some solid on the bottom. And then take a clear glass tumbler like this and fill it about halfway full with that salt water, that saturated salt water. Then, very carefully, and you might want to tip the glass sideways to do this, very carefully pour fresh water on top of that. Your goal here is to avoid mixing. So again, if you tip the glass and pour slowly, then the water comes in this way, and what you get is a glass of water that has mostly salt water on the bottom and mostly fresh water or tap water on the top. The mixing between these two layers is pretty slow. Now take an egg. An egg has a density such that it is more dense than water. So what will it do in water? Sink. But it's less dense than salt water. So if you carefully put the egg in here, your egg will float in the middle of this glass with no apparent support whatsoever. So it's kind of a mystery thing. Can fool the kids. Get them an extra week of chores if they can explain it. There's no way. Okay. Another factor that is involved in the rate of reaction, temperature. Heat moves molecules faster. And so when they move faster, they get more mixing to take place, and more mixing means it's going to dissolve faster. So if you want something to dissolve faster, put it in hot water. Even if its solubility isn't much greater, the rate at which it dissolves will be. Now, one of the most important things we have to talk about in the solution chapter is the concept of concentration. In other words, how much solute do we have? Let's go back to the case where I had a liter beaker of water and I put 1 grain of my salt in there. Okay, do I have a solution? What word would you pick to describe that solution? Micro solution, but it's pretty big, it's a liter. Okay, is there another word we could use to describe that? How about rhymes with dilute? A dilute solution, there you go. We have a dilute solution, which means what? There's a relatively small amount of solute compared to the solvent. That's a dilute solution. Now, if I pick up 4 more grains of the salt, 4 more tiny little white particles, and toss them into my beaker, stir them up, now what word would you use to describe that solution? Probably still dilute, okay? Not very much salt in there. But realize it's 5 times more concentrated than our first solution. So the terms dilute and concentrated, although sometimes useful, aren't the best discriminators. So what we prefer is usually a number. Now we have words that help us. We have the word saturated, which means what? It's full, totally full. Here's a test question that comes up every once in a while. Could you have a saturated solution that's dilute.
Yeah.
Yes. If you've got something that doesn't dissolve very much, let's take silver chloride. I told you it doesn't dissolve much in water at all. I put silver chloride in there, let's say 1 molecule dissolves into my beaker. Now it's saturated, can't dissolve anymore, but we would call that dilute. So, tricky question. So if you're looking for tricky questions on the test,
Can you repeat that one? Can you have a saturated solution?
then you have a saturated solution that is still dilute.
Okay.
We also use the term supersaturated. But in general, what do we want? As hardcore chemists here, we want a number. Give us a number. Then I can decide whether it's concentrated or dilute or whatever for my purposes. Give me a number. And we have a variety of terms that we can use to describe the concentration of a solution. We are going to define 2 of them. One of them is called percent by mass, and the other is called molarity. These are the 2 that we will talk about and do calculations with, and we'll do those calculations on Thursday. Now, you want to talk about the test. I'm pretty confident I can finish this chapter on Thursday, which means you could have the test next Tuesday. However, if we have it the next Tuesday, you won't have any chance to ask questions in between unless we meet outside of class. So I'm not necessarily suggesting that be the case. We will go on to the last chapter, which will not be on the 3rd test, okay? But we have some leeway. So I'm thinking we're looking at, well, we only have 3 possible dates if we're not counting this coming Thursday. But 11/19 would be next Tuesday, 11/21 would be the next Thursday, and then 11/26, which is right before Thanksgiving. However, the problem with this one is it's our last day of class. So if we have the exam on this day, we won't have a class to go over it. We'll have to pick it up. And,
21st.
so those are the parameters.
What do you mean the last day?
It's the last day
It's
of
the
class.
last day of class for us. Classes end on December 2nd, and that's a Monday. And so
And when is
Tuesday
our-
before